Hi, in the previous class we had discussed about GCD, some properties of GCD. Now we will encounter a very well-known problem in number theory which is called the Chinese remainder theorem. Okay, so it's a very old problem. It was posed in the first century AD by Sun Tzu. Okay, the basic problem was to find a number which satisfies some system of congruences like this. I have to find a number x which gives remainder 2 when divisible by and divided by 3. The same number should give a remainder of 3 when divided by 5. It should give a remainder of 2 when divided by 7. So there are many variations to this problem. So idea is there will be some congruences and there will be some numbers, and you have to find a number which actually gives these remainders when divided by these two numbers. Okay, so the numbers will vary here. Only thing is that it is actually a system of, you can see that it's a system, that means there are many equations are there, system of linear congruences. So we will check whether it has solution, and if there is a solution, how to find the solution. That's what we are going to discuss in this class. Okay, so we are going to do this more formally here. So before that, look at this here. These numbers here, 3, 5 and 7, as you can see, they are actually they are prime numbers, but we are relaxing it. We are going to take them as relatively prime. So we will be considering only relatively prime numbers, and we will be considering the congruences depending on these two relatively prime numbers. Okay, so let us try to define this problem more mathematically. Okay, so suppose you have some numbers are there, for example n1, n2, etc., nj, which are relatively prime. Relatively prime means their GCD is actually equal to 1. It is written 0 here, so no, it's 1 here. So GCD of ni nj is equal to 1. And what would be GCD of ni comma ni? It is nothing but the same number itself. Okay, so G0, that means GCD of ni nj is equal to 1 for I not equal to j. So I am taking these relatively prime numbers, and I am going to take my n as n1 into n2 into etc. nj. So I may use small n or capital N. It actually means n1 into n2 etc. nj. Okay, and I am going to so these are non-zero numbers. If it is 0, actually the result would be trivial. So I am taking non-zero numbers here, and also I am going to consider the I have to find a solution x which satisfies this. X is equal to some a1 into mod n1, x is equal to some a2 into mod n2, where a1 and n2 can be any numbers. Okay, so it can be any numbers, I don't know. So it depends upon the problem. Okay, so in our earlier problem, I had chosen a1, a2, etc. as 2, 3, 2 here. So it can be any number. So this is the general problem which I am going to do here. So this is my setting. So what the Chinese remainder theorem says that according to the conditions of the setting, that is if your ni's and nj's are relatively prime, then there will be a solution to the system. There will be an integer solution to the system. That will prove it now. So before proving that now, what it says, additionally it says that if there are two solutions, suppose x as well as y are two numbers which satisfy all these congruences, then this x comma y, which will actually be congruent to each other modulo n. Actually x is which will be congruent to y mod n, as well as one more thing they are saying, suppose your x is a solution to the system and suppose some y is congruent to x mod n, then y also would be a solution to the system. That means any two solutions of the system will actually be congruent to each other. Actually, essentially that means they are actually unique up to congruences. Okay, so so this is actually a uniqueness statement here. That is, if you have two solutions x comma y, then actually x and y will be congruent to each other, and if x is a solution, any number which is congruent to x also will be a solution. That is the meaning of these two statements. Okay, so before proving the existence of a solution, we will prove this uniqueness. It's much more easier. Okay, suppose x and y are two solutions. So what do we mean by x and y are two solutions? That means x will satisfy all the congruence. X is equal to a1 mod n1, x is equal to a2 mod n2, right? X will be equal to aj mod nj. And similarly, y, if y is a solution, y will also satisfy this. Y is equal to a1 mod n1, y is equal to a2 mod n2, and y will be equal to aj mod nj. So what does this actually mean? This actually means that n1 divides x minus a1, right? And n1 divides x minus a2. Okay, n2 divides x minus a2, and similarly nj divides x minus aj, and here it means n1 divides y minus a1, n2 divides y minus a2, and nj divides y minus aj. Now if you take the difference, so you know that if you take difference, you will be getting x minus a1 minus y minus a1. So what is that actually? It is actually x minus y. So according to property of congruence, if n1 divides x minus a1, if n1, so if n1 divides m, n1 divides m, then n1 should divide m plus n, m minus n, linear combination of mn. So using that property, you will be getting n1 divides x minus y. Similarly, n2 divides x minus y. Similarly, nj divides x minus y. And also, all these things, n1, n2, etc., nj are relatively prime. So you know that if a divides c, b divides c, and if a and b are relatively prime, a, b divides c. So using that result, I will be getting n1, n2, etc., nj divides x minus y, or n divides x minus y, which means that x is congruent to y mod n. So that means if you have two solutions, they will actually be congruent to each other. That's what we discuss, uniqueness. Okay, and again, suppose x is the only, suppose x is a solution, and suppose y is congruent, suppose x is a solution, suppose to this problem, and y is congruent to x. Okay, so I have to show that y is also a solution. Can you show that? That is also trivial here. It's a very simple thing. So you know that y is congruent to x. Okay, and x is congruent to a1 mod n1, right? So what can I say? So y is congruent to x mod n. That means n will divide y minus x, or n1, n2, etc., nj will be dividing y minus x. That is actually, this means actually n1 is a factor of y minus x, so n1 will divide y minus x. Okay, or it means y is equal to x mod n1. Also, it is given to you that x is equal to a1 mod n1, right? Because x is a solution. Now, if you translate this, this means that x minus a1 is divisible by n1. So if you just add up these two, you will be getting n1 divides y minus a1. That is, y is congruent to a1 mod n1. Similarly, you have n2 will divide y minus x, because n divides y minus x. So if n, that means n2 is a factor, n2 will be dividing y minus x. And also you have x is congruent to a2 mod n2. That means x minus a2 is divisible by n2. So you can see that n2 should divide the sum of them also. That means n2 should divide y minus a2. Y is congruent to a2 mod n2. That means y also will be satisfying all these congruences. So any number which is congruent to a solution will also be a solution. Okay. So all the solutions will be actually be congruent modulo n to each other. So all the solutions are unique up to the congruences. So that's the uniqueness part. Okay. So all these things will actually be meaningful only if the solution exists. So how will you show that the solution exists? Okay. So before that, first of all, we have shown that if there are two solutions, we have shown that if there are two solutions, they will be congruent to each other. And also if there is a solution, any number which is congruent to this number, the solution will also be a solution. So we have only shown the uniqueness. We have not shown that solution exists. Now we are going to show that the solution actually exists. Okay. So consider my congruences. X is equal to a1 mod n1, x is equal to a2 mod n2, and my x is equal to some aj mod nj. So I am going to show that solution exists here. Okay. So before that, what is my n? My n or small n is actually be n1 into n2 into etc. nj, n3 into etc. nj. Okay. So look at this. So what can you say about n1 and n divided by n1? What can you say about them? So what is n divided by n1? N divided by n1 is nothing but you just divide by n1 here. So it will be n2 into etc. nj. And each of them are relatively prime, so there will be no factor of n1 here. So n1 and n1 in n divided by n1 actually, their GCD will actually be equal to 1. Okay, is that clear? And similarly, what would be n1 and n by n2? What would be the GCD of these two? Now n divided by n2 will always contain n1 only. So their GCD, their common factor is always n1 is there. So definitely their GCD will be n1. So n1 will be dividing n divided by n2. So these are some simple observations which we can make. Okay. But you know that your ni and n by ni, they will have no common factors and their GCD will always be 1, because I am just cutting out that ni factor from this expression. Okay. Now, since GCD of n1 and n by n1 is equal to 1, you know that GCD can be written as a linear combination of the factors. So I can write, I can find some scalars, lambda 1 n1 plus some mu 1 n by n1 which is equal to 1, because GCD of n1 and n by n1 is equal to 1. Similarly, lambda 2 n2 plus mu 2 into n by n2 is equal to 1, because n2 as well as n by n2 are relatively prime. Similarly, going on, I have lambda j nj plus mu j n by nj will actually be equal to 1. Okay, because these scalars are there, because we have know that a GCD can be written as a linear combination of the two numbers. Okay, here the GCD is just 1. Okay, so if I consider, so these numbers will be key to my solution. If I consider, if I define a1 is equal to mu1 n by n1 and a2 is equal to mu2 n by n2, like that, my aj is equal to mu j n by nj. Okay, what can you say about a1 and n1? What can you say about n1 and a1? You know that it is lambda 1 n1 plus a1 is equal to 1, right? Lambda 1 n1 plus a1 is equal to 1, or I can write this as a1 minus 1 is equal to lambda 1 n1, or I can say n1 divides a1 minus 1. n1 divides a1 minus 1. Similarly, n2 divides a2 minus 1. Similarly, n3 divides, on a similar note, n3 divides a3 minus 1. Same idea. Okay, but if you consider some other number, for example, if I take n2 and a1, what can you say about that? Now, you can see that a1 will contain n2. Only thing is that this n does not contain n1. n1 has been cancelled out. n2 will contain a2. Is that clear? So n2 will be dividing a1. So you can say that a1 is congruent to 0 mod n2, because n2 is definitely dividing 0, dividing this a1, because this a1 contains a factor of n2 by itself. So that means n2 divides this, therefore a1 is congruent to 0. So the remainder will be 0. Okay. So what can I say generally? Generally I can say that ai is congruent to 1 mod ni, right? And ai is congruent to 0 mod nj, where I not equal to j. If I is not equal to j, it will be 0 mod nj, and if it is same, it will be 1 mod ni. Okay, so what I need a solution. So these are my ai. So I need a solution which satisfies this. X is congruent to a1 mod n1. I have to construct solution like this. X is congruent to a2 mod n2 and x is congruent to aj mod nj. Now if you look at ai, it is ai is congruent to 1 mod ni. So what happens? Suppose if I take a1 is congruent to 1 mod n1, right? So if I multiply, but I need a solution which is x is congruent to a1 mod n1. So if I multiply both sides by a1, it will be a1 will be congruent to a1 mod n1. Is it clear? Because you know that n1 divides a1 minus 1, therefore n1 will divide a1 into a1 minus 1. So a1 into a1 will be congruent to a1 mod n1. Is that clear? Now what can you say about other numbers? This a1 into a1 will be, already a1 is congruent to 0 mod n1, so a1 will be congruent to 0 mod n2, because a1 is congruent to 0 mod n2, so a1 into a1 also will be congruent to 0 mod n2. Okay, so if you consider a1, it will satisfy this first condition. Okay, but it will not satisfy the second condition. So what I will do is that I will take, to satisfy the first condition, I will consider a1 into a1. To satisfy the second one, I will consider a2 into a2, like that. To satisfy the last one, I will consider aj into aj. So this is how I construct the solution. I will be constructing solution like this. Now let us check it. Okay, so let us check what is the solution. Now, what is a? A is, if you consider for a now, you can see that if you take the first one here, so it will be a1 plus a2, right? That's the definition, a2 plus etc. plus aj. You can see that it is congruent to, for mod n1 here, for a1 I will be getting, when I divide by n1, it will be a1 Okay, for A2, this already n1 is a factor of A2, so the remainder would be 0 here. Again, for the next one, the remainder would be 0. So when I divide A1 by A1, the remainder would be A1. Okay, when I divide A2 by N1, the remainder would be 0. Similarly, when I divide AJ by AJ, the remainder would be 0. So I will be getting this as A1 mod N1. Okay, similarly, when I divide by N2, it will be okay, A1 equal to A1 mod N1. So if you consider another number A2, okay, so if you divide by A2, you will get, if you consider this number, this factor will be given here as, this will be for A1. When I divide by N2, the remainder would be 0 here. For this I will be getting A2 here, because A2 is congruent to A2 is congruent to A2 mod N2, so that factor I will be getting 0 here. Other everything I will be getting 0, so it will be finally I will be getting A2 mod N2. So you can see that this number defined in such a way will satisfy all the congruences. So this is my solution. So how I am defining the solution? Solution is being defined as A is equal to A1 plus A2 plus etc. AJ. This is how I will be defining the solution. Okay, so don't lose the big picture here. How have I constructed here? So my solution for this problem is, if you look at this problem here, my solution to this problem is A is equal to A1 plus A2 plus etc. plus AJ. So I have to remember how to construct this. Okay, so these A1s are coming from this here. You can see here, A1s are coming from my problem itself. They are actually the reminders which you require. So in this problem, A1 should be, my A1 would be, small a1 will be 2, small a2 will be 3, small a3 will be a2. Okay, so that is how I define A1. And what is my A1 here? Capital A1. How I have defined my capital A1 here? So you go back to the equation here. So this one is like capital. So basically, what you will do is that you, for defining my capital A1, first go for the first equation, that is your N1, consider N1 and N by N1. Okay, and since the GCD is 1, you have to find numbers lambda 1 N1 plus mu 1 N by N1. This quantity will be your A1. Okay, how will you construct N2? Go to the second ones, N2 and N by N2. Since they are relatively prime, I can find lambda 2 N2 plus mu 2 into N by N2. You have to find mu 2. From this I will be getting my A2. So this is how you construct the solution. Okay, now let us look at a concrete example and we will try to construct it here. Okay, so look at this problem here. So it will take a little bit of work, but still. So if you look at this problem, I know that the solution is of the form, what solution? A is equal to A1 plus A2 plus, since there are all three equations, it will be A3. And what is my A1, A2, A3? My A1 is 2, my A2 is 3 and my A3 is 2. You can see these reminders are my A1, A2s and A3. Okay, how to construct my capital A1? So capital A1 is, first you consider the first number. So there my N1 is 3, N2 is 5, N3 is 7. Okay, so my capital would be 3 into 5 into 7. So in the first case I am going for 3 and that is N1 and capital N. Capital N is 3 into 5 into 7 by N1. So I will look for 3 and 35. These are relatively prime. So you can find an equation. For the next one I will go for 5 and that is N2 and capital N by N2, that is by 5. So I will be looking for 5 as 5 and 21. Okay, next one is I will go for 7 and 3 into 5 into 7 by 7, which is nothing but 15. So 7 and 15. So I have these three numbers. Then I will find out the GCD relation. Okay, so the GCD is 1 here. So I have to find constants in such a manner that 3 lambda 1 plus 35 mu 1 is equal to 1. So this will be my capital A1. Okay, similarly 5 lambda 1 plus 21 mu 1 is equal to 1. So it's just 5 lambda 2. So 5 lambda 2 and my 21 mu 2 will be equal to 1. So 25 lambda 2 and 21 mu 2 is equal to 1. So this will be my A2, and similarly 7 lambda 3 plus 15 mu2 mu3 is equal to 1. So this will be my A3. So you have to construct A1, A2 and A3. So just using by trial and error, you can try to construct it, or you can go for Euclidean algorithm and find it out. So now can you just think of some relations here? So by trial and error, if you know that 3, so okay, 3 I am going to bring. So basically 3 into 12, 36 minus 35 is equal to 1, right? So if I consider my lambda 1 is equal to 12 and mu 1 is equal to minus 1, I will be getting 3 into 12 minus 31 is equal to 1. So my mu 1 is minus 1. So my A1 is actually equal to minus 35. Clear? Similarly, go for next one, 5 lambda 2 plus 21 lambda mu 2 is equal to 0. So can you think of a relation like this? So you know that 5 into minus 4 minus, that is 20, minus 20 plus 21 into 1 is equal to 1. So minus 20. So I'm just using trial and error to find out the coefficients. That will be much more easier here. So you have that 5 into minus 1, 21, 1 is 1. So this is my A2. So my A2 is 21. Okay. Similarly, can you think of something here? Very simple. You bring a multiple of this thing to near to this 15 here. So you have 7 into 14. Okay. 7 into minus 7 into, okay. So basically minus 7 into minus 2 minus 14 plus 15 into 1 is equal to 1. Minus 14 plus 15 into 1 is equal to 1. So here if you take this 15, so A3 will actually be equal to 15. Okay. So these are my A. So this is this. Now how will I construct my final solution? My final solution is A1 into A1 plus A2 into A2 plus A3 into A3. So my A1 was 2, so it is A1 into minus 35. So minus 70 plus A2 is 3, A2 into 21, that is 60 plus 63 plus A3 is 2, so it is 15, so 13. Okay, so just do this. So this minus 7. So I think it is minus 70 plus 63 minus 7 plus 23. So I am getting my number as A23, which is a solution. Let us check whether it's a solution. So what happens when I divide 23 by 3? When I divide 23 by 3, the remainder would be 2, correct? When I 23 by 5, the remainder would be 3, correct? And again, when I divide 23 by 7, the factor would be 2. Okay, so this is one way of constructing this. So this is a solution. So I hope it is clear. So don't forget to remember that how A1, A2 and A3 is obtained from that GCD relation. So this is how you solve the Chinese remainder theorem. Okay, so I hope it is clear. Thank you.